So, first, not at all what we're doing today, but, well, what we're doing here, but a friend of mine, Ethan Wong, whose name is not here, that's a little odd, he'll be holding a thing right after this, if you're interested, where he just talks about his ThinkPads. And also, he's fun to talk to, and also, he's one of the few people that I know personally who has used Rust in his job. He's written some software for Argonne National Laboratory that ran in continuous integration, so something like GitHub Actions, that sort of thing, that was written in Rust. I don't know much more about it except that it was written in async Rust, which is something we will not get to, but which is a great deal of fun and tedium and, it's like all the problems we're learning how to solve, but more. And I'm sure he would like to talk about that at some point, or at least give you his vibes because he on it because he likes it. But anyway, it'll be chill. You don't have to do any of that. You can just like look at the ThinkPads. It'll be in CDRLC 1413, and I'll be there. And so yeah, let's focus on drop and refactoring the code. And I know a lot of people have taken a break, so I will try to be mindful of that. And if I go too fast, please let me know. Oh, I'm sorry. See ya.
Thank you.
Let me close the door at least partially. So our list so far is this struct here, this type that has just one field, the head, and then that head is a link, which is either empty, so that's like the end of the list. If our list is empty, that's what it is, or it's more of a box of node. So this is, a generic, like a template in C++, if you've seen that, or a generic in Java, if you've seen that, in general concept. A box is, I need my editor to like me. Here's the real test of Z. I know some people have totally understandable issues with Rust Analyzer, but I'm going to try to install it right now. Rust, okay, but no, it's not. Okay. Oh, it is. It just asynchronously loads. Lovely. Okay, this isn't actually all that helpful, but it does say it's a pointer type that uniquely owns a heap allocation of type T. So that means when this box goes out of scope, it gets freed, that this node gets freed, right? Does anyone need more clarification? I went over it a lot more before. Okay, yeah, hell yeah. And then a node is just an element and then another link. So you can see how we have a list overall here. Is anyone confused by this? Because this is kind of weird. Okay, hell yeah, it's just an option. Yeah, optional thing. And then we have some methods. You do that with this impl block, so it's sort of floating, unlike a lot of other languages where you have to define it, or at least declare them in the same block as you declare the type. But we just say, okay, with a list, you can make one like this, and you can push onto it like this, and there were shenanigans here, and there were other shenanigans here. And I think the shenanigans here are like very similar to the shenanigans here. They're both covered in the book. The shenanigans are mostly this replace function and why we need it. And they're also covered in the last recording. And then we were talking about how to implement drop for it. So drop is what Rust has instead of destructors. They are sometimes termed destructors. I think she talks about them as this is always annoying. I think she talks about them as destructors in the book. I'm showing off my little web app that automatically redirects to where we want to go, but I didn't. Okay, and I didn't bookmark any. Okay, if I used this correctly, it would be great. Anyway, Yeah, so the problem, okay, so it's a destructor, effectively. It's also a trait, which is a broader feature in Rust, um, which is kind of like an interface in other languages. Um, and technically, we don't have to write an implementation of drop at all because the box will clean itself up. When our list goes out of scope, like when we wrote some testing code last time. So we have this list, and then eventually it'll go out of scope, right? Everything will get cleaned up on its own, but the problem is the code that the compiler writes to do this is very mechanical and very simple and not actually good in this case. So what happens is effectively the compiler writes this code, even though there's an important thing that's wrong with this, but the logic of it is correct. What the compiler does is it says, okay, so what's a list? A list is a link, right? So when you lose, like when a list goes out of scope, we have to drop its link. Okay, we also defined links, so the compiler has to figure out how to drop that. It says, okay, if it's empty, we don't actually have to do anything, right? But if it's got, hello. If it's got more to it, then we need to drop the node inside. And we also, like this is, yeah, the compiler also generates this because actually the way generics work in Rust is that each like instance of a generic is a different, like requires different implementations for everything to be generated. So it has to write this specifically for box of node because nodes are different than anything that the standard library knows about. So it says, okay, what do we do here? We need to drop the pointer inside the box. What we specifically need to do is we need to drop that type, right? Because node might own something. So the reason why we're calling the destructors is because these types might own pieces of memory or might have something special that they need to do. And then we need to actually clean up this allocation, right? If this were just a box of I32, we wouldn't actually have this step because an I32 doesn't need anything to clean itself up. And this is the problem. So there's this concept of tail recursion. Does anyone not know what tail recursion is? It's totally fine if so. Does anyone know what? Okay, hold your hand up if you feel like you know what tail recursion is. Okay, these are very different answers depending on how I ask the question. That's totally fine. Yeah, so tail recursion is this neat property where certain kinds of recursive functions are actually optimizable to be a loop and like semantically are a loop. So we can look at this. In this case, it's a pretty simple tail recursive function in some sense. It's not super simple because it's not even obvious that it's recursive if we just look at it, right? Because self.head.drop is calling drop on link, not drop on list. But let's pretend that we're calling drop on ourselves or on some other instance of a list in this, right? We just have a foo that then calls itself. That's tail recursive. It's also a bad idea because it'll infinitely loop, right? But it's tail recursive because the last thing this function does is call itself. The last thing this function does is recurse. So the term tail recursive comes from the fact that the recursive call is at the tail of the function. Why that matters is because if it's the last thing we do, then we don't actually need to keep track of this stack frame anymore. So we can reuse this stack frame. So effectively, the machine code that gets generated by a smart optimizing compiler that knows about tail recursion and can do this, which is many of them, is the same machine code that would be generated as a loop. It doesn't like have the overhead of a function call necessarily. It just jumps back to where it was because the notion is if this function were like correct, and had, like, if our simple version of this function that just calls itself were correct and had a base case, you need to think about what happens in the case of that base case, right? If it had a base case, and it was tail recursive, then that base case could just return. That base case could just return the. Sorry. If it had a base case and it was tail recursive, then when it gets to that base case, the whole stack just returns at once. We just return whatever we've calculated to return in the base case straight back out. We don't have to return and then return and then return, because each function call along the chain didn't actually have to do anything after the recursive call. So that's the clearest way in my head that it turns into a loop. So this is mutual recursion, so it's a lot trickier, but what's important is if everything ended with a call to the recursive thing, then this whole situation would be tail recursive. So on its own, this isn't a problem. On its own, this isn't a problem, because this is the last thing that we do in this case. Is anyone confused by this match syntax, by the way? Okay, sure. Yeah, no, that's fine. So have you seen a switch statement? Yeah, so this is like a hyper-powered switch statement in some sense. If you just look at this bit, it's basically a switch statement. Because it's just talking about, okay, if star self is this constant empty, then run this little block of code, right? Here, it's doing a little bit more. It's if star self is something that is link : : more, then extract the boxed node from it, and then we can use that in this block of code and run this block of code, right? So what matters is that this is like, for executions of this function that end here, the recursive call is at the end here, right? So we could have turned that into we could turn this whole thing into just a loop so far. Down here, we have a problem because we can't turn the whole thing into a loop, because this is a recursive call, but we still have to do something after it. And the reason why this has to be made, and I got real confused about this in the last video, so if you want to see me get confused, see the last video. The reason is because fundamentally this pointer might have a destructor that it needs to run, right? So the point is, we're cleaning up this node, this box of node, but this node might point to more. So actually we have to clean that up first, which is why we have to recurse and actually keep track of where we are so we can finish cleaning up this node after we've cleaned up our next. And that means that our stack can grow in size proportional to the number of items in the list, and one of the damn reasons why we were putting the items of the list on the heap in the first place was so that we didn't have to do that. So this is a big issue if we let this auto-generated code stay our implementation for drop for our linked list. It's just not really doing the job. So instead, we have this code, which I am not actually going to go over right now. I think I did an okay job talking about it last time. I had made one mistake, though, which was very simple. Well, that's funny. I must have undone my fix, which is good. So this was the mistake I had made. And the tricky thing here, okay, so what's this code doing? This code is saying, these are the shenanigans, right? It is still helpful to look at these two for more information on the shenanigans, but the shenanigans are the way we fix certain problems with the kinds of manipulations we want to do on memory when we're doing something with a linked list is often we temporarily make our head empty. And the reason we do that is because even though we don't want our head to, okay, in this case, it's fine if our head is empty. In some other situations, it doesn't make any sense, right? We're pushing onto the list, but first we make the head empty. That's like, okay, for now, our list is completely empty for some reason. That's sort of silly. But the reason is at least it's a valid state, and the Rust compiler likes reasoning about valid states. It would be really irritating or it would be really tricky to make a compiler that figured out, oh, your code is correct, even though temporarily you have two pointers to the same thing. The main thing that it's trying to protect you against is the fact that many things can panic, many things, which is the equivalent of throwing an exception, right? If you panic and you're in an invalid state, then everything goes kaput. So we keep things in a valid state by initially making our head empty. So like we're effectively holding a null pointer in the head here. In fact, I think that's what the machine code does. Then this while let is sort of funny. We iterate until this pattern, which is the same sort of thing you could write to the left of these arrows, stops matching. And that means we keep pulling this next out. And then each time we replace the next, so we sort of destroyed the list by forgetting about the rest of it for now, in some sense, and just deleting this node. And then we go to the next node. So we don't have to remember anything about the previous nodes. We're actually destroying it, like chewing it up from the head, as opposed to going all the way back and then finishing our job. So this is actually a loop. Does that make sense? So our stack doesn't grow wildly. The easiest way to prove that is there's no recursion at all. And, you know, the compiler doesn't invent recursion, which is nice. But we have a problem here. It's actually really simple. I didn't get a chance to look at my video again. Maybe I got more confused and this makes more sense. But the problem is when we're replacing our next, this should not be next. That's what she calls it. When we're replacing our current boxed nodes next to be empty, we need to mutate it. And we can't because this is a binding that is a variable that we've introduced. Just like any other binding in Rust, it is not mutable by default. One of the reasons I'm saying binding is it's not just because that's what the docs say. It's because binding is explicitly agnostic as to whether it's modifiable, right? So we need to say we can change this node, and that fixes it. And now if I cargo test, I really hope it doesn't blow up. It doesn't blow up, and we wrote those tests. I mean, she wrote them and I copied them. And they're well commented and all that, I think. But my display scaling is off, and that bothers me. Okay. Can this get bigger? No. This can never be bigger. Okay. Does anyone have any questions? Awesome. So I feel like it's both a sign that I was going pretty slow and a sign that that this is working all right for people who are joining now. So the next list, does she say anything fancy? Yeah, okay, this is okay now. That was bad. Or kind of sucky. So we will de-invent the wheel. We will make our list able to handle any element type. Oh, I'm jumping ahead. I'm sorry. What I want to say is that I didn't give the full story. I love this section. This is the only time she uses this like graphic at all. And I think it's a really good exercise or thing to consider. She does give the answer. I'm not going to click on it right now. But this is, again, kind of a place where we weren't doing things the listy way. Like, yes, now we aren't chewing up the stack, but we do need to store and, in fact, copy the contents of the node. And I think I talked about this in a meeting that wasn't recorded, but thankfully it's all in the book. I'm not adding that much. The whole real point of having a linked list is if it would be expensive to copy the things around, right? It's faster for insertion. It's faster for splitting things. These are benefits of the list, but if it's okay to copy things around, you should just use a vector. The benefit is that the nodes can stay intact when you're not touching that particular node, right? With a vector, sometimes you have to copy as the vector grows, is at least one instance of it. So this still kind of sucks because this mem replace it copies, wait, no, where does it suck? How is it different? Wait, maybe this doesn't suck. Maybe she fixed this. I think this doesn't suck. No. It's very similar to while let some self.pop, which is certainly simpler. How is it different and what performance issues could result from it? Okay, so it sucks in some way. I think it sucks by copying things. What I don't want to get down to this rabbit hole. I just want to point out that there's an interesting rabbit hole here. And it's totally fine if you just click to expand the answer, but it is cool to think about it. So we'll learn a bunch of shit, but for now we'll learn a little bit about this and a little bit about this and eventually maybe this. So let's just make another file. And I think the first thing she does is copy everything. Oh, yep. And maybe my editor is going to be really nice and, yep, say that there's a problem with this, which is that, you know, everything that determines what our project actually is starts with main. That's where the compiler looks. So we need to declare this module in there. So all I did was like command period, which is a common shortcut, and then it inserts it. Particularly observant readers may have noticed that we actually reinvented a really bad version of option. This link is just the choice between having something and not having it. And that's the option type which we saw at least briefly here, because it's the standard way to, like, we knew we had invented this link. We didn't want to hand other people links. And we wanted this method to always work even when there's nothing in the list. So we have to sometimes say, hey, you reached the end of the list. You can't pop something else off. Link is just option of box of node. It's nice not to have to write that. And yeah, we're not, okay, I already went over that. It has, but option as a sort of general concept actually has stuff that is, I don't know if it's totally non-trivial to write. It's possible to get it wrong. So it's nice that the Rust standard library wrote it for us, so we should use it. And then I don't know if I'm going to replicate all this, because it's kind of, oh, no, I will, because this is actually the useful thing. This is called a type alias. It doesn't actually introduce a new type. Link is just a synonym for option of box of node. But so like a function that takes a link and a function that takes an option of box of node are usable in exactly the same cases, which is a double-edged sword, honestly. But because this is all internal to our code, I think it's fine, especially because this isn't public. But yeah, so we'll just replace this with that, and now we have problems. But nothing that a little bit of, honestly, this sort of thing can fix. Link more should be, that's not how you do it. Should be replaced with. And let's not actually do link : none. Let's just do none, because the nice thing about option is that this stuff is built in, and we don't have to do the namespacing. So also link : none should just be none. And link : more should just be some. If that exists. What did I do wrong? Oh, I messed it up badly. link colon more should be some. Link colon empty should be none. This always scares me, even though it shouldn't, because this is very simple, but it's just because I know that, like, the computer does know on some level, or the computer could be taught the actual thing I want to do, which is not just replace this text blindly. It just happens to be correct, right? There's something about the language that would be, you know, if there were a tool that knew more about the language, maybe that would be more likely to be correct. But let's see if this works. Okay. Yeah, so this business of replacing something with none is so common that, I mean, it is trivial, but mem replace is sort of an ugly function. But I mean, fundamentally, we're not changing the concept of it. We're doing the same thing, right? We're still temporarily invalidating our list in terms of like what we want to be true, but we're making sure that it stays in a safe state. Take, I think, is an obvious enough name. Does anyone have any questions as to why we're calling it take when we're taking the thing out of it? Okay. So all these things turn into and this one I just have to remember, it's boxnode.next.take. And this is, I think, actually useful to point out that the dot operator is doing kind of a lot here, right? Because the difference between these two things is that replace is what's called a free function. That's just mostly a term for syntax in that it's not a method, right? And this dot take is defined if Rust wants to. Okay, Rust Analyzer is really unhappy that the syntax of this doesn't make any sense, so it doesn't even want to. Huh? Oh. I was doing the wrong thing. That's why it doesn't want me to go there. No? No field box node oh, it's not self.box node, right? So box node is not actually on our, it's a local variable. That's my bad. Okay, take is a method, which Rust makes kind of obvious is quite similar to just a function that takes a thing, right? That takes a parameter by having you write it like this, by actually saying ampermute self in here, right? This is a small abbreviation of self : ampermute capital S elf, which would be fully writing out how you'd write it as a parameter. Capital S self is just a synonym for the type we're currently describing. So it's really similar, but the dot operator is doing this borrow for us. Takes this borrowed next, but we don't have to ever borrow it with ampermute. Because this dot operator is doing it for us. I don't know. I think that's kind of neat, and it's also something to keep in mind. Honestly, I see both sides of it when I was learning about this, and I still see it as Rust is being a little fancier than I'd love it to be here. I like thinking more explicitly about memory, but the trick of dereferencing or taking references with the dot operator is so nice that I'll mostly take it. Like, it's good. And that's not really what Rust is about. Rust is about the underlying safety of it all. So that seems kind of mostly irrelevant. So does this work? And also, did I get rid of all the replaces? Yes. Okay. Second, match option of none resulting in none, and then something resulting in something else. So this code doesn't actually work, but the notion is we're doing, what if we did something here that like took X and turned it into Y, right? This sort of thing is also really common. We can use the map function on option, and if anyone's familiar with lists and their map function in lots of other languages, like a vector or an array in JavaScript has a map function. The fact that they're named the same thing is not an accident. You can probably see how it's kind of similar. So is anyone not familiar with the map function on a JavaScript array or on something similar? Sure. Yeah, okay. Please bear with me. The notion is if we have, I'm mentioning JavaScript, so I might as well just use the JavaScript concept. What the hell? How do you, okay, so if you press shift, then it really doesn't matter what, okay. This is an array in JavaScript. If I wanted to get this array but turn it into an array with that was sort of transformed in any way that I can think of, I can supply a function that will operate on each element of this array and return a new element. In JavaScript, you can write a lambda function, which is like a function you don't even give a name, like this. And here's where the code goes. And here's like, we take one parameter, we're naming it X, right? And if I just said, return X here, then actually it already ran my code and it said you get the same array, right? But if I return X plus 1, it runs this function against each one and adds something to it. So I guess the intuition here with the relationship with map is just there's something inside the option. In option, it's a variable number of things. It's 1 or 0. In an array, it's a variable number of things. It's 0 or any number, actually. It's any number. That's the simpler way of putting it. So map applies to the thing inside it, right? Also, there's fancy shenanigans where this is actually way more useful and pretty if you understand monads. And I certainly don't know how to explain them. But this is a functional programming concept. At their core, the math of doing this on an abstract data type that works like an array is very similar in useful ways to doing that on an option, and there are other related things that you can do with them as well. But that is beyond me. So yeah, this mapping is where our code gets a little bit more rusty, but also a little bit potentially harder to read. I think it's the right call, and it's certainly the right call for the tutorial, because you will see map. So instead, we just copy this bit in here. Right, so I have to explain that this is also us creating a lambda function in Rust. This is creating a function that we didn't give a name, and I somehow screwed it up. I think, what did I do? Mismatch closing delimiter. That'll do it. And now we have a problem because it doesn't matter to match here.
I gotta go to lab.
Okay, yeah, see ya. Cannot find value first. Right, so I had captured that, not captured that. This was a binding that I introduced in the match statement, but to keep it all simple, I'll do that. And now we have an issue. Which is fascinating. Okay, am I even in the right method? Yes, I am. So, what did I do differently? We take the head, and then based on what it is, like if there's something there, the idea of this is we, give it a function that will transform it if it's something there. The problem is, right, map actually abstracts over this creating the new option as well. Here, we created a new option down here. And I'm still doing that here. So the compiler is telling me the mismatch types are that I have too many layers of optionality. I don't need to create this option. Map does that for me. The idea is I transform the thing inside it, and then map handles putting it back into an option. Okay. Hooray. I love unit tests when it's easy. um, let's move on to actually improving the code's behavior. So generics. Yeah, this is, maybe I started saying this, but like I was saying, lists make sense for big elements because you don't want to, the whole point is the nodes can stay in the same memory location for as long as possible. That's also why this layout is kind of funky, like why we have like 3 types when all we really wanted to do was expose 1. But so far our list could just store integers, so now we're going to be messing with generics. Does anyone immediately know, this is just a random question and I'll explain any results. Does anyone immediately know why these are called generics and not templates? Or what the difference between generics and templates are that is meaningful? Also, who has seen generics before in some language? Java, okay. Who have you two seen? You've seen generics?
Yeah.
Have you've seen generics?
I think sometimes.
Okay. In what?
C.
In C? C does
No, sorry, that's macros.
That's what?
Macros.
Macros. Okay. So the fundamental thing that generics are trying to solve is basic, like this is kind of the prototypical example. We want to define a type that can apply, that is actually like a family of types, where, you know, we want to define it once and make it work for any contents, right? Usually that's what it's about. And the reason why we have this problem at all is because we don't have dynamic typing. Otherwise, we could just say, I've defined a list, and it doesn't actually care what's inside it. You know, Python would be totally happy with that, right? JavaScript too. So generics are the more common and certainly more modern solution to this problem, which is where we say that we parameterize a type. We say that it now has a parameter, which is another type. We say, you know, it's not enough to say I have a list. You have to say I have a list of something else, right? C++ has templates that are quite similar, and fundamentally I think that same description applies, but the difference is in focus and in one little quirk. So there are a bunch of implementation differences. Java does generics very weirdly. Rust and C++ do generics basically the same, where for like a list of an i32 is actually different machine code from a list of an i64 or a list of my own type, like person or whatever. And the reason that actually makes sense is because manipulating those different types requires different shenanigans, different operations. And it's not too expensive to add more code, though sometimes it can be expensive. It can actually, I think it was one of the major performance issues with Rust in the Linux kernel, was that like adding more generics, as opposed to the way some of this stuff would have been written in C, was causing there to be more code and causing there to be cache misses on the code. But Java can do things differently, but conceptually, the central conceptual thing is that this generic, like it's only going to be possible for me to write this this way, like writing this particular text here, if this implementation of a list doesn't care about anything about T. It just knows that there is a type T. Whereas in C++, you can get away with all sorts of shenanigans. I just want to very briefly show this. In C++, I could do something like, oh boy, JavaScript is feeling extra slow today. I think this is how you do it. Like, I'm just trying to define a class that holds a T inside it. You know, so now I could theoretically create, is this how you do it? I think you have to do that in C++. Okay, it compiles, right? So we have a class, and we can have a function that, like, I mean, let's just say it does something, right? It says hello world, right? It doesn't even do anything to the myT. And this doesn't work right. Let's say this is void because I don't actually feel like doing anything else. Okay, so this works, and I can even create a foo f. And this is, you could write this, the equivalent of this code in Rust as well. It would look something like and then we'd have some impl that would just like print hello world. I'm not even going to bother to write it. You could, it would look like this, right? So far so good. And of course we can do like f.myfunc. And it doesn't work. Oh, right, because I didn't say what kind of foo I want. So C++ does still want to know, so let's just say that I create a foo of an int. It's got an int inside it. We don't care. And it's private. I forgot basic syntax things. And what do you need to do here?
You do public and then the colon. And then
Oh, right.
yeah.
That's me having Java brain. Okay, so it works, right? So what if I did this? What if I said, actually, let's print myT plus 2. So I'll promise you, even if you don't know the C++ syntax, I think I can promise that this actually, is a way to print hello world followed by the variable myT plus 2. I think that works. Are there any problems you see with this right now? Roberto, are there any problems you see with this?
T is a generic, so like
Yes.
It doesn't know the sum operator how to handle the object,
Yeah.
I suppose.
So does that make sense? The notion is like, I'm defining this. It should work for any T. I didn't say it can only work for T's that you can add. So what the fuck does this mean? Actually, this works. Now, I don't know why it printed that. Oh, because I didn't initialize this. That'll do it. Okay, this works. So what if instead this was a foo of, okay, let's take this out of the equation. Let's say, let's just pretend we were initializing it, or whatever, forget about this. What if I had a foo of a string, right? What do you think will happen when you compile this?
It shouldn't work.
It shouldn't work.
Because at compile time, it's actually instantiating like the function myfunc for the type string. And so
Yes.
string doesn't have sum operator implemented, I think.
Wouldn't it be the concatenation?
I think it is a concatenation. I forget so strings plus, if you added two strings together in C++, you would concatenate them. But we're not adding two strings together, we're adding a number to a string.
Yeah.
I don't think that's implemented in C++. It's definitely implemented in JavaScript, where it'll turn the integer into a string and then add it on. But yeah, so we have a problem, except I didn't actually name string correctly, so that's my problem. And then we have a problem, exactly this. Yeah, we don't know how to, it's so many shenanigans that are, I think, less common in Rust, these particular sorts of shenanigans. But whatever, so many shenanigans. But importantly, right, as is probably already obvious because of what I did before, right, let's pretend that I am the library author. I just wrote this. This compiles fine. What the hell? It doesn't mean anything unless we have the ability to add integers to our weird T. This is something that, in my experience, every time someone uses the word generic to describe something, is not something you can do. You can't implicitly start using things as though they're whatever you want, right? So Rust has generics, even though they work a lot like C++'s templates under the hood. This is the contract they have with you. This, we couldn't start adding to T in our implementation, which is good because the most common usage, certainly the most common basic usage of generics or templates, is for container types, where you don't really care what the thing is. So it's nice not to have the foot gun, right, when we don't need it. You just make everything a little pointy, and suddenly your code is generic. I think I'm just going to get one paragraph down, because this is always fun when we get errors. So a list is a list of T. Links are links to T. Links to T have nodes of T inside them, and nodes, we don't know what's in them. And then we save it, and I can run cargo test, and I still get the compile time errors, which are nice, and it tells me how to fix all the problems. I don't know if it was telling her. It wasn't, apparently, so Rust got much nicer, I think, but it's also a little bit I don't know, these days I'm skeptical because I hope that people aren't just blindly doing this. I hope they're also understanding it. But you can, right? The problem is that it's it makes sense to us to just say, oh, let's talk about our types as though they're generic, but we have to talk about them like that consistently. We have to implement this for all T. I think Rust will let you instead be oh, a list of I32, it has these special methods in addition. So that's cool. But we have to be explicit and say we're implementing it for all T. But then, you can think of this T as sort of like a variable. This is sort of a declaration of it, and this is a usage of it. It's just a type. So here, this isn't a declaration of it because we're not declaring list of T. So we have to say this is what it is. I think that's the syntax. Yeah. Or not. Expected this what? Okay, what is it telling me? Oh, it's telling me this. Okay, first let's just fix this. And then let's... This is what happens when you don't actually know how to use Vim, but you want to use the Vim keybinds because they make you seem cool. You delete things with 2 keystrokes, one at a time. Okay. So definitely we're having this issue. I wonder if that will fix everything? That doesn't make sense because I think, okay, so now we have a different issue. Right. This is not a declaration. Like I just said, you have to declare it in this sort of funny way, which is maybe not familiar. But I think we still have issues, right, because we need to implement it on everything. And then we have a problem because some of our methods are not taking taking I32s still and returning I32s. So we need to not do that. We're just matching everything up wherever we saw I32. Now it's T. I think that one's fine. And then I think our problem is kind of, okay, so this was hinting at an error, I think just because Rust was confused about what we were doing up here, but this was actually sort of an error that thankfully Rust doesn't usually give us. It says type annotations needed for this variable. It doesn't say that anymore, and that's because in general, Rust is smart enough to figure out, oh, you're pushing ints to this, so this is a list of ints. If I hover over it, figured it out. If I was pushing strings to it, it figures it out. So I think this, that's about it. I do want to show one more thing, or two more things. One, if you missed a bunch, or if you're just curious for more resources, obviously the Learn Rust with Entirely Linked Lists is interesting, but this is the chapter in the Rust book that I think is most interesting. And this is by a guy named Faster Than Lime. I think I shared something by him at one point. It's more of a review than anything, but it's just like, here are all the syntax, and he talks a lot about the semantics in ways that you might not just see if you were just looking at syntax. I went through this, like it just blasted through it earlier today, and I thought it was pretty good. It explains some like software engineering-y things that you probably don't know, but they're probably don't need to know, but they're neat about when exactly you can implement traits. And yeah. And then one last thing. You're probably all aware of it, but I'll be holding an event on Monday on a way of using concurrency not to make code faster, not to make different parts of your program able to progress independently of each other. They'll still very much synchronize with each other, but to make algorithms look much more like the code you wanted to write. Much simpler with much fewer shenanigans. Specifically, data structures like binary trees can be made simpler in this way. And if you don't want to come or whatever, it will be recorded. And also, this blog post is one of the best written blog posts I've ever read. So there's that. And now I'm going to go look at ThinkPads. Oh, I did want to add just one tiny more thing. 1 second. One tiny more thing is that drop is a weird trait. Not just because it has like fancy semantics, like it means this is how you should destroy instances of my type, but because the way traits are typically written, like named, in Rust is with the verb that is the thing you can do with them. So it's not addable. It would be addable in Java if it were an interface. It's just add, so you can add it. And sometimes traits can have multiple methods, right? We've only seen drop and add that each only have one, but you can sort of think of, oh, I would pick like the word for the thing that you can do with things of this type, right? So typically, what it means for something to implement, say, add, is to say, okay, you can add it to something. You can actually specify what the right-hand side is, so they don't have to be the same. But you can add it to something, right? So if this type implements add, you can add it. I think they're missing a trick here. This is just my personal opinion, and maybe I don't know if it's more just me yapping, or maybe it's helpful, but you can drop everything, but only certain things implement drop. It's not obvious. Only the things that you or that someone wrote an implementation of drop for that had to be manual are known as implementing drop, even though everything can be dropped. So before we wrote this, even though our list did all sorts of like fancy things when you dropped it, it did that recursive, calls and then they returned again, it still wouldn't have implemented drop. Why does it matter when things implement a trait? Because the actual way that we can make generics fancier, if we wanted to, where like maybe we do want to do something with the element in here, is we could say that in order to have a node of type T has to be add. And then we could start adding them. But this is still better than just having a node of ints, because now it works for any integer width and anything else that implements add, right? So I just thought I'd finish that story and describe, like, when I was learning it, it was confusing to me that it's like, wait, drop is actually the weirdest way to introduce the concept of how we name traits because it breaks the rule. Almost everything else that's named with a verb, actually only the things that implement that do that. Anyway. What the? Okay. Mac OS.